Hello, I'm Giuseppe Buonaiuto. Thanks for giving me the chance of speaking here. In this poster, I'm going to describe to you the work that we have been recently doing at the ICAR CNR in Napoli, entailed in the spoke 3 of the project itself, called Multilingual Multitask Quantum Transfer Learning. Here we demonstrate that embedded knowledge coming from pre-trained deep learning large language models can be effectively transferred into a quantum classifier, which shows good performance is either comparable or slightly better than their classical counterpart, with a further reduction of the number of parameters. Furthermore, a qualitative linguistic analysis is carried out, which elucidates 2 points. First, the lack of language dependency in the quantum models and the ability to discriminate with higher precision subtypes of linguistic structures. What are the objectives of this work? We want to integrate quantum algorithms with AI-based NLP models for testing the limitation and the capabilities of quantum machine learning for NLP, taking advantage of higher computational capability potentially coming from quantum computing, and hence learning with fewer data and generate lighter model. What is the idea of quantum transfer learning? It's similar to classical transfer learning. We have pre-trained classical models that are used to represent in a form of real valued vector data specific of certain task. Here, rather than using a classical model to manipulate and extract information from this embedded representation of data, we use a quantum circuit, which is composed of parameterized gates, whose parameters are then iteratively updated via a learning rule, a classical learning rule, in the standard machine learning fashion. There is a one step that is further required to this algorithm to take place, which is the embedding of the classical vector representation into a quantum vector state, which is crucial to manipulate the information with a quantum computer. This is made possible by a plethora of techniques, among which we choose amplitude embedding, which basically consists in storing the embedding vector into the amplitude of a quantum state. What are we actually doing in our experiment then? We extract embedding vector using BERT and Electra on 2 tasks. The acceptability judgment, which is a syntactic task in the sense that it deals with classifying whether a sentence is grammatically acceptable or not, and sentiment analysis, which is well known and standard, which deals with classifying positive tweet to negative tweet and is intrinsically a semantic task. These 2 tasks are carried out both on English and Italian to demonstrate the ability of the model of performing multi-language classification. So we extract the embedding vector via the pre-trained model. We entail this vector into a quantum state via amplitude embedding, and then this vector are manipulated via a parameterized quantum circuit in the form of a strong entangled ansatz, which is here described in this figure. Measurement is performed on the final state, and the results of the measurement are compared with the ground truth label of each dataset. We use for this purpose 4 datasets, COLA and ITA-COLA for acceptability judgment, and Sentipolka stand for 2 for sentiment analysis. At the end of the training process, we evaluate the SHAP values, hence we perform an explanative AI approach for decide whether or not the algorithm is capable of discerning different subtypes of linguistic structure, and if or not, the quantum circuit is sensitive to language. The result shows that, on average, quantum algorithms and classical algorithms are mostly similar, with the exception that for Electra quantum, on semantic and on sentiment analysis task, quantum computing is performing better than their classical counterpart. SHAP values analysis, on the contrary, revealed that quantum models are sensitive to sentence complexity for syntactic tasks, while they are most robust than classical when dealing with the quality of the data source, meaning that if the dataset is less polished, quantum algorithms are able to extract better information than classical algorithms. And this is elucidated both by the metrics that hereby are showed in this table and by the qualitative linguistic analysis on each sentence structure. In conclusion, there is the need of incorporating syntactic information in the quantum circuit when dealing with acceptability, judgment, or similar syntactic tasks. The result here presented can be found in these papers here. In particular, the last one is being submitted to Quantum Machine Intelligence and is currently under review. Thank you for your attention.